All right, you guys. So for the last part of this chapter, I just want to reiterate something that I said at the end of the last video, which is the idea that the mass of a star is really what determines um, what's going to happen to the star, like how it's going to burn itself out. And the reason is because the more mass you have, the more pressure you can have inside of that core of the star. Um, which means you can fuse higher elements beyond helium um, to carbon and beyond carbon. Okay. So towards the end of a star's life, you're going to have what is a late red giant phase, right, where you have the core continues to collapse on itself. The production of hydrogen to helium is essentially slowed. Now you're doing helium to carbon inside the star, which produces less energy, which causes the star to collapse. The star becomes dimmer, right? It becomes smaller and dimmer, okay, and moves a little bit back towards the main sequence. Um, at that point, this is where stars start to differ. So there are a few different types of outcomes based on how much mass is actually there. First of all, we're going to start with the less massive stars, the smaller stars. Things on the order of the sun and below, thereabouts. Once all of the hydrogen's been burned up to make helium, helium will then start to fuse into carbon. And once that hydrogen starts to fuse into carbon, you start to get a lot of instability on the surface of the star, right? The core is contracting more. There's less of that energy output from the fusion of hydrogen. And so the outer layers of the star will sometimes just get sloughed off, essentially, pushed away into space. Okay? And what's left over is a giant ball of gas and elements that we call a planetary nebula. And that's kind of what you see in this picture here. The star died out, and what's left over around it is the gas and things that have been drained off the top of the star. At that point, the carbon core will contract to what's known as a white dwarf, which is just a really hot chunk of leftover star core, if you will. And once that white dwarf cools, over time you can sometimes get what's called a brown dwarf. It's not mentioned here, but it's just essentially a white dwarf, a chunk of carbon left over from the death of a star. You call it brown because you can't see it. It doesn't produce light like a white dwarf would. Okay. Now, that being said, if there's more mass, then you get more gravitational contraction. You get things compressing more as that energy from the fusion starts to drop out, right? So as you get up into that carbon level, now you're not generating as much energy from fusion. So that star starts to collapse and collapse even more. Now, if there's enough mass, the star can continue to fuse atoms. What that means is it'll go from carbon and fuse to I'm not sure what the next step is. Somewhere between carbon and iron. Not 100% sure where that next step of stellar production goes, but it will step up through carbon until it gets to, it may be one of those crash course videos, until it gets to iron. At the point of iron, you cannot fuse iron anymore. Iron sits at the bottom of a curve that is essentially related to the energy released when you fuse two atoms less than iron or split an atom bigger than iron. both generate energy. In order to do that to iron, you have to put energy in. If you want to fuse iron into something else, you have to put energy into it. If you want to split iron into something else, you have to put energy into it. And iron is the bottom of the barrel in terms of energy per nucleon, which basically just implies how much energy you get out of those nuclear reactions that are occurring inside of the stars. Hydrogen, by far, the biggest. You get the most energy out of that. Helium, maybe the second most, and then it goes down further and further. But if there's a lot of mass there, that core will continue to collapse beyond carbon. If it's not a lot of mass, carbon's the end step. But it'll continue to fuse until it gets to iron. And once it gets to iron, you can't fuse it anymore. You can't fizz it. You can't split it. So all the energy is used up. Now at this point, you completely lose. Once fusion stops, you completely lose the balance between the gravity of the gases of the star and the core of the star itself. And in some cases, the outside gases of the star will collapse all at once to the core and explode outwards. And that's called a supernova. And supernovas are how every element greater than iron on the periodic table is formed. When those giant supernovas happen, all of that energy, then there's enough energy put in to put that iron together into something else, and you start getting heavier and heavier elements. Notice iron's only 26 on the periodic table, so there's a whole another 80 some odd elements above that that are only generated in supernova explosions of stars, until you get to the ones way high up in the periodic table that are man-made. Now, the supernova is true for heavier, more massive stars, but there's still two remaining choices as to what's going to happen. If you have a kind of massive star, mostly massive, somewhere between 1.4 and 3 solar masses. So that's if the core is that much. So the core is about 1 to 3 times the mass of the sun. Okay, not the whole star, just the core. What you wind up seeing is that there's enough pressure and gravitational pressure to fuse the protons and electrons inside of atoms together. And when you do that, you get neutrons. And that gravity will cause that to happen throughout the star, and you get what's called a neutron star. And a neutron star is essentially just a big giant ball of neutrons that are extremely compressed, super, super dense, extremely compressed. So much so that a neutron star could fit, like, in the United States. They're not that big in terms of size. But they are extremely massive. It's like all the mass of that star in this little small object, or smaller object. One type of neutron star is what's known as a pulsar. These are just neat because they rotate very quickly, and put out. They sometimes put out electromagnetic waves, depending on if they're collecting mass from other stars, binary systems, things like that. But these are neat. I actually did some research on one of these 17 years ago or something like that. And based on the satellite data, you could measure the period of the rotation of that pulsar. And it was something like 42 milliseconds or microseconds. It was fast. That star went all the way around multiple times per second. Now, if the core of the star is greater than 3 solar masses, then that gravitational pressure, it just basically runs unchecked. And everything collapses to the point that it's so dense that light cannot escape. And we call that thing a black hole. The fact that light can't escape comes about from the fact that the escape velocity of that particular object is greater than light. Okay, so if you want to launch a rocket from the surface of the Earth into space, then you need to be going at least 11.2 kilometers per second, and that will get you out of the pull of Earth's gravity. for a black hole, you'd have to be going greater than 3 times 10 to the 8th meters per second, or 3 times 10 to the 5th kilometers per second. So 30,000 kilometers per second, fifth. 300,000 kilometers per second, as opposed to 11.2. And so that's why we call black holes, because they're literally so dense that the escape velocity is greater than the velocity of light. So this is just a brief picture of sterile evolution, right? So they all start off as a nebula that forms into a protostar. When that thermonuclear fusion turns on, you get a main sequence star. And then from there, things start to kind of branch out. Low mass stars go from white dwarfs to this cold lump of carbon, like I said, that are sometimes called brown dwarfs. Mid-mass stars will still form a red giant, but then will essentially just slough off their outside into a planetary nebula and leave a white dwarf behind. And those high mass stars go to supernova, and depending on the mass at that point, either go to a neutron star or a black hole. Just a couple of things real quick. Now that we've talked about stars in general, I want you to recognize that most stars are found in binary systems. They're not found single, alone, like we see the sun. The sun's alone. Okay, most of them are found in binary systems. If you look in the sky, you'll kind of see these. I think I mentioned this in one of the other videos, but if you see a star that kind of switches from red to blue, that's generally a binary system. The closest star to the sun is a binary system. So the sun in that way it's not unique, but it is different, not average. On average, most star systems contain multiple stars, or 2 stars. Now, when we take stars, we can basically gather them together into what we call clusters. Okay, clusters are essentially tens to hundreds of thousands of gravitationally bound stars, all kind of in the same region. They all generally share a common origin, so you get some kind of stir up in that particular galaxy that starts causing a bunch of stars to form. Right, so it comes some kind of shockwave passes, and then star, 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 over and over and over again. And you can actually see this occur in some places, where you will see, I believe it's the Crab Nebula, that as over time the gas has started to fade away, and you can start to see new stars forming. Now, when we collect all these stars together, we collect them all, at least in our general region, into a galaxy. A galaxy's, the book refers to as the basic unit of the universe. There are billions of galaxies, with billions and billions of stars in each one. One of the coolest things you can see is in images of what's known as the Hubble Deep Field. So the Hubble telescope, you guys are probably too young to remember, went up first, didn't work all that well. The mirrors were wrong. I went back and they fixed them. Then you point the Hubble telescope at any region in space, and you let it just sit there and look at it for a while. And what you see are all these tiny bright lights. And if you zoom in, every single one of those lights is a galaxy. And all of those galaxies contain all sorts of different stars. And the Hubble Deep Field will make you feel very tiny in the universe, because there is so much to see. Actually, I'm just going to pause this lecture real quick and go pull up a picture for you. Okay, so I just pulled this up real quick so you can see this. But this is just an image of the Hubble Deep Field. And each of these things that you see, those are galaxies. Right? That's a galaxy, galaxy, definitely a galaxy. Right? Some of them turn on their sides where you can see them like you're looking at them from the top down. And some are flat so that you can only see them from the side. But every one of these is a galaxy. And this is just one region of space. They just point it in one direction, and that's what you see. You can do this in every direction. In every direction when you look in the sky, this is what you'll see. If you had a super powerful telescope. You cannot see it with just your eyes. Okay, so when we talk about galaxies, we then build them into what are known as clusters or galactic clusters, and then superclusters. Okay, this is really just grouping together regions of the universe that we can visibly see and things like that. So our galaxy is the Milky Way. All right, it's very hard to see. It's as visible as a diffuse band on a dark night. You'd have to be in a really dark place to see this. Okay, you can, in some ways, kind of see it, but this is essentially the galactic center. Right, we're in an arm of a spiral galaxy going around this galactic center. Billions of stars, some of them found in galactic clusters. You can kind of see this if you can see this part of it. In the southern hemisphere, we really miss out in the northern hemisphere. In the southern hemisphere, they have what are known as I think it's the small and the large Magellanic. It's named after Magellan. I can't say his name. It's a Magellanic Cloud or something like that. I'm saying it wrong. But it's just a little cloud of stars in the sky. We can't see those here. This is essentially kind of what our galaxy looks like. All right, we've got this spiral arms going around. Okay, and we are located in one of those spiral arms way out here. There are other different types of galaxies. The closest one is the Andromeda Galaxy. Okay? Andromeda is what's known as an elliptical galaxy. Elliptical galaxies are basically just like an ellipse of stars. That don't have a spiral shape like what you see in the Milky Way. Okay. In some places you'll see these two separated, and some you won't. A spiral looks like the one from here. This would be a spiral galaxy. Right, we have those spiral arms. A barred galaxy or a barred spiral is going to have a thick line in the center, and then the arms come out of that after it. So it'd be like having this piece and then like arms coming out. Okay, so they're still similar spirals in some cases. And then you have what's called just irregular, and that's just all the stuff that doesn't make any kind of reasonable shape. So Andromeda is interesting, A, because it's closest to us, and that closest galaxy is still 2 million light years away. But not just that, Andromeda is on a crash course with the Milky Way. Over time, these two will run into each other and collide. Now, you might think that collision is going to cause, rampant destruction and things like that, but there's so much empty space between galaxies that galaxies can collide without them ever really interacting. They could collide with each other, and two stars never hit each other. Okay, so the last little bit of this chapter just talks about the ideas of cosmology and the ideas of how we understand how the universe formed. Okay, the way we understand the formation of the universe is based on the Big Bang Theory, which is just saying that the universe formed from a giant explosion, essentially, around 14 billion years ago. There's some evidence for that. It's not just like we made it up. Okay, you can measure the microwave background radiation. This is basically like the temperature of the universe. And as the universe cools, scale back to figure out how long ago it was really hot. We see a large-scale expansion that you would expect from things moving outwards. We also notice that almost every galaxy that we look at, or every star, they're all moving away from one another. Everything's spreading out. Okay? The only thing that's different is Andromeda, and it's because it's close to us. here it's mentioning the relative abundances of elements. What that means is if the Big Bang Theory occurs, then we know that hydrogen will be the first atom to form, helium after that. Um, and so what you would expect is that you see most of the universe would be hydrogen, some of it would be helium, and a little bit of it would be the rest of the stuff, and that's exactly what we see. So 70+% of something is hydrogen, and so on. So that's what they mean by abundances. We can predict that based on the Big Bang Theory and look and see that it matches up. Now, the question then becomes, will the universe eventually expand forever, or is it going to come back down and collapse in on itself? Right. So, expansion forever into like what is essentially known as a heat death, where everything just cools and dies, or do you wind up with a big crunch where everything goes back to like the Big Bang initially before everything comes back into one place? This is just a little bit of ways of imagining how the universe would look, or how the universe could look, whether it's going to go back to a big crunch, or whether it's going to expand at a constant rate, or whether it's going to accelerate as it expands. I'm going to attach just another video that talks a little bit about the end of the universe, and that I think is really interesting, and that should help you understand this just a little bit better too.